Quadratic inequalities are solved much the same way as the equations, by factoring. The zeros that we find are called boundaries or boundary points. And we test between the boundary points, so not on the boundary points, between them, to see which intervals are true. In this case, this first one, we have x squared. Think of it like x squared equal to 121. We would solve this by factoring. I'm going to subtract 121 over. We get x squared minus 121. We're going to leave it as greater than or equal to 0. This is a difference of two squares. 121 is 11 squared. So we get x minus 11, x plus 11. And so our boundary points are where it's equal to 0. That's going to happen at x. So boundary points, x equal to positive and negative 11. Okay, what this does is it creates three intervals. We're going to have one from negative infinity to 11, then one from negative 11 to 11, and then finally one from positive 11 on up to positive infinity. And all we have to do is test a point in each interval, or test an x value in this case, to see which one is true. So it's easiest, I find it's easiest to test very large negative and very large positive values. But let's just test something like negative 20, for instance. Negative 20 is around here. And you plug it into this equation, right? We have negative 20 squared greater than or equal to 121. This is going to be 400 greater than or equal to 121. And that's a true statement. So this is true. So that interval is a good one to have. Always test 0 whenever you can. So plug in 0. 0 squared is greater than 121. No, that's not true. And finally, we can test right. Positive 20 is over here. Positive 20 squared is 400. And that is greater than 121. So that is a true portion. So our solution is going to be the interval negative infinity to negative 11 unioned with the interval 11 to infinity. We do not include the false interval, which was between negative 11 and 11. And in this case, we do include the endpoints because we have greater than or equal to. So I actually should be writing brackets around negative 11 and 11 because that includes the endpoints or the boundary points in this case. Okay, for the next one, same kind of process. Let's get one side equal to 0. That's going to give me 25x squared minus 10x plus 1 less than 0. Okay, factoring the first side, right? AC method is 25 times 1 minus 10. This is going to be negative 5 and negative 5. That's going to give me 25x squared minus 5x plus 1. First two terms, I can take out a 5x. Next two terms, I can take out negative 1. And you can see I get 5x minus 1, 5x minus 1, which are actually the exact same expression. And that gives us only one boundary point. The boundary point is when it equals 0. This happens at 0 when, if you were to put that equal to 0, right, 5x minus 1 equals 0. That happens when x equal to 1/5. That's our only boundary point. So our interval is going to be just 1/5. And we only have to have two intervals to check. We have 0. Let's check 0. And let's check some large positive values, I mean like 10. Okay, plugging 0 in, I'm going to use this expression here to test. Plugging in 0, we're going to get 0 squared is 0, 25 times 0 is 0, minus 10 times 0 is 0. We get 1 is less than 0, which is not true. So this is not true for an interval. Let's try 10. 25 times 10 squared minus 10 times 10 plus 1. That's going to give us 100, so 2500 minus 100 plus 1. Okay, less than 0. That's going to be some large, I mean, this is what, 2401, which is not true. This is not true either. And since the inequality is a strict inequality, that means we do not include the boundary point, so 1/5 is also not included. And so we've excluded everything. There is no solution for this interval. Now, just like in linear equations, we can graph this thing on the graph by setting equal to 0 and then changing. So in this case, we're going to look at this one and look at this one here. We're going to change the 0 to y. I'm going to change the 0 to y. Change the 0 to y. And now we're going to graph these functions on the graph. And since y we changed from 0, we're asking when is this thing, when is this one greater than or equal to 0, and when is this one less than 0? So for this first one, I just had it flipped around a little bit. If I graph that, you can see the decimals will actually shade the appropriate regions. And all we care about is what the x values are, not the y value. That was introduced, so we don't really need to worry about the y. And you can see that it shades this side of -11, which is what we had. We had this side shaded, and we shade this side of +11. So all the positive values that are greater than 11, and all the negative values that are less than -11. But we also include the boundary points. That's seen by this solid line that's graphed here, the solid red line. So -11 and 11 are included. That's how you can read the graph. Now for the next one, if we graph this, you can see that it's graphed everything down here, and it has the dotted line on the boundary points. And the boundary point itself is at 0.2, which is the same thing as 1/5. But since we have a dotted line, that means we do not include the boundary point. And that means that the x values, none of them are shaded on this side, none on this side, and we do not include the boundary point, so there is no solution for this inequality. All right, give it a try in number 1. Now, rational inequalities are solved similarly. We're going to factor everything, but boundary points happen from both the numerator and the denominator. So we need to make sure we look at both of them. On top, I can factor that down into the AC methods, 3 and 3. So I can immediately factor that down into x plus 3, x plus 3. On bottom, that is going to be, let's see, 18 and -9. So it's going to be -3 and -6. So the bottom factors down into x minus 3, x minus 6. And our boundary points are the zeros from the top and bottom. So it's going to be -3 from the top. That's twice, but that's fine. On bottom, we get +3 and +6. So we have 3 boundary points. That means we're going to have 4 intervals. -3, +3, and 6. So we can, of course, test the points. We can test something like -10. We can test 0, test 4, and test like +10. And all we have to do is plug it into here. So you test -10, -10 plus 3. So -10, -10, -10, -10. And just simplify the statement down. We're going to get, for this interval, we would get, let's see, -7 times -7 over 7 times, or sorry, it's -13 times -16. There's 4 negative values there. They all cancel. 2 cancel, 2 cancel. We get a positive value, some positive value. And that's what we're looking for. When is this thing greater than 0? So this is a correct interval. Let's test 0. So plug in 0 into there. 0, 0, 0, and 0. We're going to get 3 times 3 on the top, then negative 3 times negative 6 on the bottom. Two negatives cancel. We get a positive value here. It doesn't matter what number it is. It is greater than or equal to 0. So we have this interval is true. Okay, test 4. On top, we have two positives. On bottom, we have a positive and a negative. There's a single negative. That means this whole thing is negative. So this interval cannot be true. Finally, let's test 10. On top, we have a positive. It's 13 times 13, so it's going to be positive. On bottom, we have 10 minus 3, 10 minus 3. So that's going to be 2 more positives. We get positives all around. That's going to give us a positive answer here, and that is what we want. All right. Finally, this is greater than or equal to here, which means the boundary points are included, except the ones from the denominator. That's because the denominator gives us 0, and you can never include those boundary points. So positive 3 and positive 6 cannot be included, but negative 3 can. So we have an interval from negative infinity up to positive 3, union with 6 to infinity. All right, so for this next one, same kind of process. I'm going to subtract this so that we have 0 on one side. It's going to make things easier when checking. 6 over x plus 5 minus 6 over x minus 6. So that tells us we need to get common denominators. Just multiply by the other one. This is greater than 0. Okay, I'm going to distribute this 6. I'm going to distribute this 6 here. It's going to be negative 6 on top. So we need 6x minus 36 minus 6x minus 30 all over x minus 6, x plus 5. Combining like terms on top, we're going to get the x's cancel, and we get just negative 66. So the only boundary points we get are from the denominator. So boundary points are going to be positive 6 and negative 5. Okay, so our interval, negative 5, positive 6, we can test 0. We can test like negative 10 and positive 10. Okay, plugging that into here, we're going to test negative 10 first. We have a negative number on top. We have a negative number here. And we have a negative number here. We have 3 negatives. That means the total thing is negative. And a negative is never greater than 0. So this interval cannot be true. Plug in 0. We have a negative on top, a negative here, and a positive here. 2 negatives cancel, and we're left with a positive number, and that is greater than 0. Finally, testing positive 10. We have a negative on top and 2 positives on bottom. Negative divided by positive divided by positive, that's going to be a negative number. So this interval cannot be true as well. This is the strict inequality. It wouldn't have mattered anyway because both of the zeros came from the denominator. So these border points can never be equal. Even if this were greater than or equal to 0 here, or greater than 0, it's actually the exact same interval, negative 5 to 6, because the boundary points cannot be included. Okay, let's actually graph these things and see what we get. So this first one, we have this large interval. Everything up to 3, and then everything past 6. That's what I have here. As you can see, it's this interesting graph. The only thing that we care about, right, is the x values, And the only x values that are not shaded in is right here. And that happens at positive 3 and negative 3. Sorry, positive 3 and positive 6. 3 is negative 3 is included. Everything less than that, everything between negative 3 and positive 3, and everything greater than 6 is also included there. This never crosses the x-axis. It may get closer and closer to it, but it never crosses it. Or no, it gets closer to 1. Okay, so the next one, you can see that the interval that's shaded here is from negative 5 to positive 6. And this thing looks like it might cross it, but it actually never will. It'll get closer and closer to it, but it will never cross it. As you go to the left and as you go to the right, never crosses the x-axis. So the only interval that it's defined on is this one here, negative 5 to 6, just like we found algebraically. Okay, give it a try in number 2. Now, the same process we found for linear programming, where you're looking for the overlap of all the linear equations. This can be done for any system of inequalities. Here I have 2 linear equations and a quadratic equation. And so all we're really looking for here is the overlap. And we can find the overlap here by graphing it. So let's go ahead and graph this equation here. Everything's already got y, greater than or less than something, so we don't have to move anything around. And if we graph everything, let's okay, so that's the first one, which is y equal to 20, right? Y equal to 20 is a horizontal line, and if it's greater than 20, that means you're going to shade everything up above that line. The next one's going to be quadratic. If you graph that, it's going to be everything below this, so you can see we're right in this region here. And finally, this blue one here sets us into this kind of weird shaped region. And so that's the region that we're looking at. That's the feasible region here. You can see that it has these corner points. The interesting thing about systems of nonlinear inequalities is that you won't have all corner points, right? These are 3 corner points. But on this side, you can see that we have a rounded portion here. There is this vertex that this is called, but that's not really a corner point. It's all just a rounded portion. So you can't use the same kind of ideas from linear programming to solve these kind of things, but it's done in a similar fashion where you're just trying to find the overlap of each one of the inequalities, the shaded regions. Give it a try in number 3.